Hello, my name is Bethany Alec, and I completed this work with my colleague Michael Don. We're both from the United States Army Research Laboratory. The title of this paper is Belief Propagation for Localization Using Interagent Ranging in GPS-Denied Environments. So the motivation behind this work can be shown in this picture. We have a multi-agent system operating in a GPS-denied environment. So these agents are integrating their onboard IMU, and the uncertainty associated with their state estimates is growing over time because they're not getting any global observations. There are some members of this network that have better positioning data. Either they have better IMUs or they're able to get global observations. These are called the anchor nodes, and they are called that because they anchored the system to the world frame. In this paper, we describe a realistic transceiver model that includes the communications and the interagent ranging, which is the measurements we're using to better update the position estimates on board these systems. So in this transceiver model, we have a comm schedule, which is known a priori. We have noise, and we also have a probability of a drop measurement. So our goal is to localize all of these agents with interagent observations. So there's two sides to this problem. How do we fuse this localization with the state estimation? So some of the work being done in localization includes this multidimensional scaling, which is kind of a batch optimization, not iterative approach to finding relative localization solution. There is some issues with weak connectivity. You might have some reflection ambiguities. There's also this work being done in belief propagation and message passing, so using interagent distances to better localize nodes has been done for stationary agents. So the work being done on the state estimation side, there was an article in 2018 in IEEE Control System magazines on using a keyframe approach to observe, to navigate in a GPS degraded environment. And the uncertainty and the drift over time is represented by this banana distribution. So if you're integrating a noisy IMU and you don't have global positioning data, your position estimate drifts over time. When you update this to a multi-agent system in a three-dimensional environment, I made this picture in the bottom right, which kind of shows the problem I'm trying to solve in this paper. The red lines are the true trajectories, and the blue are the possible drifty solutions. So in this paper, we use a particle filter based approach. So you can see all these these blue particles drifting off based off the disturbance model. So let's get into a little overview of message passing and belief propagation. So ThA14 is your local evidence on your agent, and then ThA X of U is your pairwise potential, and then MTU is the message from T to U. So in this picture I show two time steps. At agent T, we have the S's sending information to T. We incorporate those messages to update the belief. Then we're generating messages based off our particles representing our probability distribution of our positions, and sending those messages to the next agents. So this is all going according to our communication schedule. So the messages from T to U are proportional to the pairwise potential evidence, the local evidence, and then all the previous messages being sent to T. So let's tie this into the motion model. So we have this nonlinear model shown here. A group of M heterogeneous agents are maneuvering in this three-dimensional environment. Each agent must be able to localize themselves with observations from the neighbors. The observations are distance measurements that arrive intermittently according to a predefined schedule. Each agent has a different level of uncertainty associated with its own localization solution, which is dictated by this process equation. So the state at agent T is the position. It could also include attitude, angular rates. Then we have a disturbance model, which is varying amongst all the agents that drives the uncertainty. And then we have the input model at agent T. So the belief propagation joint, let's look at this joint probabilistic density function. So we have the x's, the states for all of our agents, and then we have, so we have initial conditions multiplied by the link probability multiplied by the distance measurements probability, and then the motion model. So the link probability and distance measurements part are taken from the transceiver model. The interesting thing about the link probabilities, this gives you, this is where we can get negative information to update our beliefs. So if you imagine you are scheduled to talk to somebody but you do not receive that communications, there's inherent information in that loss of measurement, and we call that negative information. So it is more likely that my neighbor is further away than I originally thought, which means if you have this large distribution representing your prior evidence of where you think you are, and some of that space is well within your link probability range, then you can lower the weight of that region to update your uncertainty. So in particle filtering, this works out very well. You just take the particles that are very unlikely and you weight them lower. And then you do a resampling step. So on the right we have a factor graph representation of this, where we have a Markov chain from k-1 to k, time k-1 to k, and then this changing link connections. The dotted line are the measurements, which are changing based off the schedule. So what are these messages that we're going to be sending around? So I'm assuming that there's no angle of arrival information in this link. The belief that is represented by the outgoing messages are a function of your weighted samples. The message generated from each sample is this. MTU is equal to your current position at MU plus, so I is the particle label, plus the distance measurement, which is the true distance plus the noise from the transceiver model, multiplied by this spherical array. And so the angles are drawn from this uniform distribution to generate this sphere. So you can imagine if you have another agent that's also communicating to T, where do these spheres overlap, and how can you incorporate that into your prior to get better localization solution? So the algorithm works like this. You propagate your own belief. If messages are received, you incorporate in your own belief. If messages are not received, return your current belief. Then you set up messages to send to the neighbors. So if you're not getting information, your uncertainty is going to grow, of course. But if you're getting information, you're getting those particles, you can update your prior. Next step is, how do we do the sampling and weighting? There's many approaches to this. How do you find the intersection of these spheres in the prior? If T is scheduled to receive messages and a message is received, you weight the belief with the received messages. If a message is not received, you weight the belief with the probability that that message is dropped. So the particles that are not likely get weighted lower. And on the right, we show the probability of drop measurements. This changes rapidly based off a number of parameters listed in the paper. The one I'm showing here is the K, which is basically how many people are talking at the same time, because we're using this CDMA, TDMA protocol. So more people talking at the same time means more noise. So then step 2, we incorporate all the weights from all the scheduled messages, and then we resample samples using the new weights, and then we're done. So the results are shown here. Remember how everyone's estimates would drift into this kind of 3D banana distribution. In this scenario, agent 1, 4, and 8 are the anchor nodes, very low uncertainty. And then agent 2, 3, 5, 6, 7 have very large uncertainty to start with. The particles are really spread out. And then I turn on the transceiver, and then the messages start to get spread around, and the particles are resampled based off the transceiver model and using the priors, and the uncertainty quickly goes down. And you can see that in the covariance of the samples. Start off with very large uncertainty, lots of lost robots, and then we converge to a very low uncertainty. So the concluding remarks: we developed an algorithm for localization with positional uncertainties. We have the ability to incorporate this negative information from the transceiver model, and we used, of course, the realistic transceiver model to do this. We have some future work defined here, and that's it. Thank you very much.